The kilogram. A kilogram is the base unit of mass in the International System of Units and is defined as being equal to the mass of the international prototype of the kilogram. The avoirdupois pound, used in both the imperial and US customary systems, is defined as exactly 6,999,453,592,370,000,000 spade suit 0.45359,237 kilograms, making 1 kilogram approximately equal to 2.2046 avoirdupois pounds. Other traditional units of weight and mass around the world are also defined in terms of the kilogram, making the IPK the primary standard for virtually all units of mass on Earth. Definition: the gram, 1/1000th of a kilogram, was provisionally defined in 1795 as the mass of 1 cubic centimeter of water at the melting point of ice. The final kilogram, manufactured as a prototype in 1799 and from which the IPK was derived in 1875, had a mass equal to the mass of 1 cubic decimeter of water at its maximum density, approximately 4 degrees Celsius. The kilogram is the only SI base unit with an SI prefix as part of its name. It is also the only SI unit that is still directly defined by an artifact rather than a fundamental physical property that can be reproduced in different laboratories. 3 other base units and 17 derived units in the SI system are defined relative to the kilogram, so its stability is important. Only 8 other units do not require the kilogram in the definition: temperature, time and frequency, length, and angle. The international prototype kilogram was commissioned by the General Conference on Weights and Measures under the authority of the Meat Convention, and in the custody of the International Bureau of Weights and Measures, who hold it on behalf of the CGPM. After the international prototype kilogram had been found to vary in mass over time relative to its reproductions, the International Committee for Weights and Measures recommended in 2005 that the kilogram be redefined in terms of a fundamental constant of nature. At its 2011 meeting, the CGPM agreed in principle that the kilogram should be redefined in terms of the Planck constant. The decision was originally deferred until 2014. In 2014 it was deferred again until the next meeting. There are currently several different proposals for the redefinition. These are described in the proposed future definitions section below. The international prototype kilogram is rarely used to handle. Copies of the IPK kept by national metrology laboratories around the world were compared with the IPK in 1889, 1948, and 1989 to provide traceability of measurements of mass anywhere in the world back to the IPK. Name and terminology. The word kilogram or kilogram is derived from the French kilogramme, which itself was a learned coinage, prefixing the Greek stem of chi iota lambda iota omicron iota kilio 1,000 to gramma, a late Latin term for a small weight, itself from Greek gamma rho alpha mu mu alpha. The word kilogram was written into French law in 1795 in the Decree of 18 Germinal, which revised the older system of units introduced by the French National Convention in 1793, where the grave had been defined as weight of a cubic centimeter of water equal to 1/1000th of a grave. In the Decree of 1795, the term gram thus replaced grave, and kilogram replaced grave. The French spelling was adopted in the United Kingdom when the word was used for the first time in English in 1795. 1797, with the spelling kilogram being adopted in the United States. In the United Kingdom both spellings are used, with kilogram having become by far the more common. UK law regulating the units to be used when trading by weight or measure does not prevent the use of either spelling. In the 19th century the French word kilo, a shortening of kilogram, was imported into the English language, where it has been used to mean both kilogram and kilometre, while kilo is acceptable in many generalist texts, for example The Economist. Its use is typically considered inappropriate in certain applications, including scientific, technical and legal writing, where authors should adhere strictly to SI nomenclature. When the United States Congress gave the metric system legal status in 1866, it permitted the use of the word kilo as an alternative to the word kilogram, but in 1990 revoked the status of the word kilo. During the 19th century, the standard system of metric units was the centimeter-gram-second system of units, treating the gram as the fundamental unit of mass and the kilogram simply as a derived unit. In 1901, however, following the discoveries by James Clerk Maxwell to the effect that electric measurements could not be explained in terms of the three fundamental units of length, mass and time, Giovanni Giorgi proposed a new standard system which would include a fourth fundamental unit to measure quantities in electromagnetism. In 1935 this was adopted by the IEC as the Giorgi system, now also known as MKS system, and in 1946 the CIPM approved a proposal to adopt the ampere as the electromagnetic unit of the MKSA system. In 1948 the CGPM commissioned the CIPM to make recommendations for a single practical system of units of measurement, suitable for adoption by all countries adhering to the meter convention. This led to the launch of SI in 1960 and the subsequent publication of the SI brochure, which stated that it is not permissible to use abbreviations for unit symbols or unit names. The CGS and MKS systems coexisted during much of the early to mid-20th century, but as a result of the decision to adopt the Giorgi system as the international system of units in 1960, the kilogram is now the SI base unit for mass, while the definition of the gram is derived from that of the kilogram. Nature of mass. The kilogram is a unit of mass, a property which corresponds to the common perception of how heavy an object is. Mass is an inertial property, that is, it is related to the tendency of an object at rest to remain at rest, or if in motion to remain in motion at a constant velocity, unless acted upon by a force. According to Newton's laws of motion and the equation F equals ma when acted upon by a force F of 1 Newton, an object with mass m of 1 kilogram will accelerate a at the rate of 1 meter per second, about 1/10 the acceleration due to Earth's gravity. While the weight of an object is dependent upon the strength of the local gravitational field, the mass of an object is independent of gravity, as mass is a measure of how much matter an object contains. Accordingly, for astronauts in microgravity, no effort is required to hold objects off the cabin floor, they are weightless. However, since objects in microgravity still retain the mass and inertia, an astronaut must exert 10 times as much force to accelerate a 10 kilogram object at the same rate as a 1 kilogram object. Because at any given point on Earth the weight of an object is proportional to its mass, the mass of an object in kilograms is usually measured by comparing its weight to the weight of a standard mass, whose mass is known in kilograms, using a device called a weighing scale. The ratio of the force of gravity on the two objects, measured by the scale, is equal to the ratio of the masses. Kilogramme des Archives. On April 7, 1795, the gramme was decreed in France to be the absolute weight of a volume of pure water equal to the cube of the 100th part of the meter, and at the temperature of melting ice. The concept of using a unit volume of water to define a unit measure of mass was proposed by the English philosopher John Wilkins in his 1668 essay as a means of linking mass and length. Since trade and commerce typically involve items significantly more massive than 1 gram, and since a mass standard made of water would be inconvenient and unstable, the regulation of commerce necessitated the manufacture of a practical realization of the water-based definition of mass. Accordingly, a provisional mass standard was made as a single-piece, metallic artifact 1,000 times as massive as the gram, the kilogram. At the same time, work was commissioned to precisely determine the mass of a cubic decimeter of water. Although the decreed definition of the kilogram specified water at 0 degrees Celsius, its highly stable temperature point, the French chemist Louis Lefebvre-Ginot, and the Italian naturalist Giovanni Fabbroni, after several years of research, chose to redefine the standard in 1799 to water's most stable density point, the temperature at which water reaches maximum density, which was measured at the time as 4 degrees Celsius. They concluded that 1 cubic decimeter of water at its maximum density was equal to 99.9265% of the target mass of the provisional kilogram standard made 4 years earlier. The same year, 1799, an all-platinum kilogram prototype was fabricated with the objective that it would equal, as close as was scientifically feasible for the day, the mass of 1 cubic decimeter of water at 4 degrees Celsius. The prototype was presented to the archives of the Republic in June, and on December 10, 1799, the prototype was formally ratified as the Kilogramme des Archives, and the kilogram was defined as being equal to its mass. This standard stood for the next 90 years. International Prototype Kilogram. Since 1889, the magnitude of the kilogram has been defined as the mass of an object called the International Prototype Kilogram, often referred to in the professional metrology world as the IPK. The IPK is made of a platinum alloy known as PT10IR, which is 90% platinum and 10% iridium, and is machined into a right circular cylinder of 39.17 mm to minimize its surface area. The addition of 10% iridium improved upon the all-platinum kilogram of the archives by greatly increasing hardness while still retaining platinum's many virtues: extreme resistance to oxidation, extremely high density, satisfactory electrical and thermal conductivities, and low magnetic susceptibility. The IPK and its 6 sister copies are stored at the International Bureau of Weights and Measures in an environmentally monitored safe in the lower vault located in the basement of the BIPM's Pavillon de Breteuil in Chevret on the outskirts of Paris. 3 independently controlled keys are required to open the vault. Official copies of the IPK were made available to other nations to serve as the national standards. These are compared to the IPK roughly every 40 years, thereby providing traceability of local measurements back to the IPK. The meter convention was signed on May 20, 1875, and further formalized the metric system, quickly leading to the production of the IPK. The IPK is one of 3 cylinders made in 1879 by Johnson Matthey, which continues to manufacture nearly all of the national prototypes today. In 1883, the mass of the IPK was found to be indistinguishable from that of the Kilogramme des Archives made 84 years prior, and was formally ratified as the kilogram by the first CGPM in 1889. Modern measurements equivalents of Vienna standard mean ocean water, which is pure distilled water with an isotopic composition representative of the average of the world's oceans, show it has a density of 6,999,999,975,000,000 spadesuit 0.999975 plus or minus 6,994,100,000,000 spadesuit 0.00001 kilograms L at its point of maximum density under 1 standard atmosphere of pressure. Thus, a cubic decimeter of water at its point of maximum density is only 25 parts per million less massive than the IPK. That is to say, the 25 milligram difference shows that the scientists over 217 years ago managed to make the mass of the kilogram of the archives equal that of a cubic decimeter of water at 4 degrees Celsius, with a margin of error at most within the mass of a single excess grain of rice. Copies of the International Prototype Kilogramme. The various copies of the International Prototype Kilogramme are given the following designations in the literature. The IPK itself, located in Chevreuse, France. 6 sister copies, numbered K1, 7, 8, 32, 43 and 47. Located in Chevreuse, France. 10 working copies, 8 for routine use and 2 for special use. Located in Chevreuse, France. National prototypes stored in Australia, Austria, Belgium, Brazil, Canada, China, Czech Republic, Denmark, Egypt, Finland, France, Germany, Hungary, India, Indonesia, Israel, Italy, Japan, Kazakhstan, Kenya, Mexico, Netherlands, North Korea, Norway, Pakistan, Poland, Portugal, Romania, Russia, Serbia, Singapore, Slovakia, South Africa, South Korea, Spain, Sweden, Switzerland, Taiwan, Thailand, Turkey, United Kingdom and the United States. Some additional copies held by non-national organizations, such as the French Academy of Sciences in Paris and the Istituto di Metrologia G. Colonetti in Turin. Stability of the International Prototype Kilogramme. By definition, the error in the measured value of the IPK's mass is exactly zero. The IPK is the kilogram. However, any changes in the IPK's mass over time can be deduced by comparing its mass to that of its official copies stored throughout the world, a rarely undertaken process called periodic verification. The only 3 verifications occurred in 1889, 1948, and 1989. For instance, the U.S. owns 490% platinum, 10% iridium kilogram standards, 2 of which K4 and K20, are from the original batch of 40 replicas delivered in 1884. The K20 prototype was designated as the primary national standard of mass for the U.S. Both of these, as well as those from other nations, are periodically returned to the BIPM for verification. Note that none of the replicas has a mass precisely equal to that of the IPK. The masses are calibrated and documented as offset values. For instance, K20, the U.S.'s primary standard, originally had an official mass of 1 kilogram minus 39 micrograms in 1889. That is to say, K20 was 39 micrograms less than the IPK. A verification performed in 1948 showed a mass of 1 kilogram minus 19 micrograms. The latest verification performed in 1989 shows a mass precisely identical to its original 1889 value. Quite unlike transient variations such as this, the US's Czech standard, K4, has persistently declined in mass relative to the IPK, and for an identifiable reason. Czech standards are used much more often than primary standards and are prone to scratches and other wear. K4 was originally delivered with an official massive 1 kilogram minus 75 micrograms in 1889, but as of 1989 was officially calibrated at 1 kilogram minus 106 micrograms, and 10 years later was 1 kilogram minus 116 micrograms. Over a period of 110 years, K4 lost 41 micrograms relative to the IPK. Beyond the simple wear that Czech standards can experience, the massive, even the carefully stored national prototypes can drift relative to the IPK for a variety of reasons, some known and some unknown. Since the IPK and its replicas are stored in air, they gain mass through adsorption of atmospheric contamination onto the surfaces. Accordingly, they are cleaned in a process the BIPM developed between 1939 and 1946 known as the BIPM cleaning method, that comprises firmly rubbing with a chamois soaked in equal parts ether and ethanol, followed by steam cleaning with biodistilled water and allowing the prototypes to settle for 7 to 10 days before verification. Cleaning the prototypes removes between 5 and 60 micrograms of contamination, depending largely on the time elapsed since the last cleaning. Further, a second cleaning can remove up to 10 micrograms more. After cleaning, even when they are stored under the bell jars, the IPK and its replicas immediately begin gaining mass again. The BIPM even developed a model of this gain and concluded that it averaged 1.11 micrograms per month for the first 3 months after cleaning, and then decreased to an average of about 1 microgram per year thereafter. Since Czech standards like K4 are not cleaned for routine calibrations of other mass standards, a precaution to minimize the potential for wear and handling damage, the BIPM's model of time-dependent mass gain has been used as an after-cleaning correction factor, because the first 40 official copies are made of the same alloy as the IPK and are stored under similar conditions. Periodic verifications using a large number of replicas, especially the national primary standards, which are rarely used, can convincingly demonstrate the stability of the IPK. What has become clear after the third periodic verification performed between 1988 and 1992 is that masses of the entire worldwide ensemble of prototypes have been slowly but inexorably diverging from each other. It is also clear that the mass of the IPK lost perhaps 50 micrograms over the last century, and possibly significantly more, in comparison to its official copies. The reason for this drift has eluded physicists who have dedicated their careers to the SI unit of mass. No plausible mechanism has been proposed to explain either a steady decrease in the mass of the IPK, or an increase in that of its replicas dispersed throughout the world. This relative nature of the changes amongst the world's kilogram prototypes is often misreported in the popular press, and even some notable scientific magazines, which often state that the IPK simply lost 50 micrograms, and omit the very important caveat of in comparison to its official copies. Moreover, there are no technical means available to determine whether or not the entire worldwide ensemble of prototypes suffers from even greater long-term trends upwards or downwards, because the mass relative to an invariant of nature is unknown at a level below 1000 micrograms over a period of 100 or even 50 years. Given the lack of data identifying which of the world's kilogram prototypes has been most stable in absolute terms, it is equally valid to state that the first batch of replicas has, as a group, gained an average of about 25 micrograms over 100 years in comparison to the IPK. What is known specifically about the IPK is that it exhibits a short-term instability of about 30 micrograms over a period of about a month in its after-cleaned mass. The precise reason for this short-term instability is not understood but is thought to entail surface effects, microscopic differences between the prototype's polished surfaces, possibly aggravated by hydrogen absorption due to catalysis of the volatile organic compounds that slowly deposit onto the prototypes, as well as the hydrocarbon-based solvents used to clean them. It has been possible to rule out many explanations of the observed divergences in the masses of the world's prototypes proposed by scientists and the general public. The BIPM's FAQ explains, for example, that the divergence is dependent on the amount of time elapsed between measurements and not dependent on the number of times the artifacts have been cleaned. Possible changes in gravity or environment. Reports published in 2013 by Peter Compson of Newcastle University based on the X-ray photoelectron spectroscopy of samples that were stored alongside various prototype kilograms suggested that one source of the divergence between the various prototypes could be traced to mercury that had been absorbed by the prototypes being in the proximity of mercury-based instruments. The IPK has been stored within centimeters of a mercury thermometer since at least as far back as the late 1980s. In this Newcastle University work, 6 platinum weights made in the 19th century were all found to have mercury at the surface, the most contaminated of which had the equivalent of 250 micrograms of mercury when scaled to the surface area of a kilogram prototype. Scientists are seeing far greater variability in the prototypes than previously believed. The increasing divergence in the masses of the world's prototypes and the short-term instability in the IPK has prompted research into improved methods to obtain a smooth surface finish using diamond turning on newly manufactured replicas and has intensified the search for a new definition of the kilogram. See proposed future definitions below. Dependency of the SI on the IPK. The stability of the IPK is crucial because the kilogram underpins much of the SI system of measurement as it is currently defined and structured. For instance, the Newton is defined as the force necessary to accelerate 1 kilogram at 1 meter per second squared. If the mass of the IPK were to change slightly, so too must the Newton by a proportional degree. In turn, the Pascal, the SI unit of pressure, is defined in terms of the Newton. This chain of dependency follows to many other SI units of measure. For instance, the joule, the SI unit of energy, is defined as that expended when a force of 1 Newton acts through 1 meter. Next to be affected is the SI unit of power, the watt, which is 1 joule per second. The ampere too is defined relative to the Newton and ultimately the kilogram, with the magnitude of the primary units of electricity thus determined by the kilogram. So too follow many others, namely the coulomb, volt, Tesla, and Weber. Even units used in the measure of light would be affected. The candela, following the change in the watt, would in turn affect the lumen and lux, because the magnitude of many of the units comprising the SI system of measurement is ultimately defined by the mass of a 137-year-old golf ball-sized piece of metal. The quality of the IPK must be diligently protected to preserve the integrity of the SI system. Yet, despite the best stewardship, the average mass of the worldwide ensemble of prototypes and the mass of the IPK have likely diverged another 6.4 micrograms since the third periodic verification 27 years ago. Further, the world's national metrology laboratories must wait for the fourth periodic verification to confirm whether the historical trends persisted. Fortunately, definitions of the SI units are quite different from the practical realizations. For instance, the meter is defined as the distance light travels in a vacuum during a time interval of 1/299,792,400 158th of a second. However, the meter's practical realization typically takes the form of a helium neon laser, and the meter's length is delineated, not defined, as
7,157,980,029,872,800 spade suit 1,579,800.29872 wavelengths of light from this laser. Now suppose that the official measurement of the second was found to have drifted by a few parts per billion. There would be no automatic effect on the meter because the second, and thus the meter's length, is abstracted via the laser comprising the meter's practical realization. Scientists performing meter calibrations would simply continue to measure out the same number of laser wavelengths until an agreement was reached to do otherwise. The same is true with regard to the real-world dependency on the kilogram. If the mass of the IPK was found to have changed slightly, there would be no automatic effect upon the other units of measure because the practical realizations provide an insulating layer of abstraction. Any discrepancy would eventually have to be reconciled though, because the virtue of the SI system is its precise mathematical and logical harmony amongst its units. If the IPK's value were definitively proven to have changed, one solution would be to simply redefine the kilogram as being equal to the mass of the IPK plus an offset value, similarly to what is currently done with its replicas, e.g., the kilogram is equal to the mass of the IPK plus 42 parts per billion. The long-term solution to this problem, however, is to liberate the SI system's dependency on the IPK by developing a practical realization of the kilogram that can be reproduced in different laboratories by following a written specification. The units of measure in such a practical realization would have the magnitudes precisely defined and expressed in terms of fundamental physical constants, while major portions of the SI system would still be based on the kilogram. The kilogram would in turn be based on invariant, universal constants of nature. Much work towards that end is ongoing, though no alternative has yet achieved the uncertainty of 20 parts per billion required to improve upon the IPK. However, as of April 2007, the US's National Institute of Standards and Technology had an implementation of the Watt balance that was approaching this goal, with a demonstrated uncertainty of 36 micrograms. See Watt balance below.